Thank you. That's the most enthusiastic and largest response for a talk about assembly language in many years. You might wonder why we're talking about the assembler, and there's a reason, but I'm going to come to it. First of all, you might ask, well, why do we care about assembly language at all? So let's go back to 1970 for a quote from an IBM manual, which reads, "The most important single thing to realize about assembler language is that it enables the programmer to use all System 360 machine functions as if he were coding in System 360 machine language." Now, there's a lot of sort of dated aspects of that, but the fundamental point is right. Assembler is how you talk to the machine at the very lowest level. And in fact, even today, we still need assembly language. It used to be that all you had was assembler, and then what we called high-level languages like Fortran and COBOL came along, and sort of over time, but slowly, displaced them. And even C, for a while, was argued as being, a high-level language when you had assembler available. But we still need assembler today because of this access it provides to the machine. You needed to bootstrap your environment to get the stacks running, do switching between contexts. In the Go world, Go routine switching is all done in assembler. There's a performance aspect. Sometimes you can just handwrite code that's better than the compiler can give you. And for instance, in the math big package in the Go standard library, there's a fairly substantial amount of assembler because the core routines of that library are so much more efficient when you cheat the compiler and do something smarter than the compiler can figure out. And also, sometimes there's just features in the hardware that may be new or unusual or not worth putting in the language, but you can get at with assembler. And that includes things like some of the new crypto instructions on the current CPUs. But for me, the most important thing about assembly language is it's the way that some people, anyway, think about the computer. It's the definition of what the instruction set is, how the machine works, the way we actually think about it. So even if you're not an assembler programmer, and I hope none of you are, it's worth understanding a little bit about assembler and then just to know how the computer works. That said, I'm not going to actually talk very much about assembly language per se, and that's actually kind of the point. So first of all, many of you might not know assembler very well. So let me show you some examples in roughly chronological order. Here's IBM System 360. That's the one that quote was about. And don't worry about what it says. Just sort of look at it. There's going to be a few gestalt-y slides here. This is from the Apollo 11 guidance computer, which was all programmed in assembler. We went to the moon in assembly language. Here's the PDP-10. This is actually well commented compared to some assembler you'll find. Here's the PDP-11. This is actually part of the assembler for assembly language in Unix v6, which is, of course, written in assembler at the time. It became C later. Here's Motorola 68000. Here's the Cray 1. I like this one because it's from Robert Griesmer's PhD thesis, which brings us home. So what you may notice about all of these is that although they're all different, they're also all kind of the same. They have a very clear common structure. The assembly language tends to be in columns. There's labels at the left, instructions, operands, and then comments out at the right. The operands themselves tend to be things like registers or literal constants or memory addresses, but they're all syntactically fairly similar between the varieties of architecture. And there's exceptions. If you look at the Cray example, it's actually different. You encode an add instruction with a plus sign, like an arithmetic expression. But all that's really saying under the covers is this is an add instruction and these are the registers. So it's really the same kind of thing. In other words, if you step way, way, way back, to me at least, CPUs look pretty much the same nowadays. There are counterexamples, but most of them, and certainly all the ones that Go runs on, are pretty much the same if you ignore a lot of detail. Let's use that. Let's use that ignoring the detail to do something interesting. In fact, we can construct a common grammar for all of these machines. And the realization that we could do that was about 30 years in the making. So back around the mid-'80s, Ken Thompson and I were starting to think about what would become Plan 9. And Ken wrote a new C compiler, which actually lived on into becoming the C compiler in the Go tools up to a few years ago. And that was on a sequent symmetric multiprocessor machine for the National 32000 CPU from National Panasonic. And I think it was the first 32-bit CPU that was generally available on a microchip. But Ken did some funny stuff that made not a lot of sense to some people, but turned out to be really important for later, because that's the kind of thing Ken does. The compiler didn't actually generate real instructions. It generated what you might think of as pseudocode. And then the second program that ran on the output of the compiler, which is the linker, actually turned those pseudo instructions into real instructions. And here's a hypothetical example. We have a move instruction that's putting a literal 0 into a variable. And it might become, by the time it comes out of the linker and runs on the machine, something like an XOR of a temporary register to itself, which will set all the bits to 0, and then a store of that register into a variable. Now, don't worry about the details. It's just what comes out of what actually the machine is running might not look exactly like what we're putting into the assembler. And this process of making up what the real instructions are for the pseudo instructions, we call instruction selection. And a really good example of a pseudo instruction is the subroutine return instruction, which Ken has called ret, and which has been ret for 30 years now. But it depends what machine you're on. On some machines, it's actually called ret in the manuals, but on others, it might be jumping through a link register or an indirection through a dedicated register or other things at all. And so the way to think about the assembler is it's just a way to handwrite the pseudo instructions that the compiler is actually generating. And unlike most architectures in the Plan 9 world, the compiler did not run the assembler. It actually fed directly into the linker. So the pieces look like this. The top line is the sort of traditional architecture, and I believe is how GCC even today still runs. There's a compiler that takes the high-level code, turns it into assembly language. The assembler then generates the real instructions, and the linker puts the pieces together to build the binary. The bottom two are what the Plan 9 architecture looked like, where the assembler, in effect, was cut in half, and the first part of the assembler got stuck into the compiler, and the second part of the assembler went into the linker. And so what's flowing across that red line is kind of a binary representation of the pseudo instructions. And all the assembler is doing in the Plan 9 world is giving you a way to write textual versions of instructions that become the pseudo instructions that drive the linker. So this was actually kept up through many generations. And the Plan 9 assemblers went along with this. They were individual C programs with the at grammar, one for each architecture, and they were sort of a suite, but they're all different programs. Each one was written fresh. They shared code, but not really. It was kind of messy. And when Go started to happen in the, when was that, 2007 we started, the Go compilers were added to this pile of funnily named programs. 8G and 6G were the Go compilers. And they used the same model. They fit this middle line here on this diagram. And the separation, the way it was done, actually had a lot of advantages for how Go was built under the covers, but I don't have time to go into that today. In Go 1.3, we had an idea that we really wanted to get rid of all the C code and move to a Go implementation, but it was going to take us a while to do that. But we started the process with the Go 1.3 release, which began by Russ took a big chunk of the linker and pulled it out and made a library called liblink, a big piece of which was called what we call the instruction selection algorithm. Nowadays, this library is called obj, but it was called liblink then. And then the compiler used liblink to generate the real instructions from the pseudo instructions in its intermediate representation. And there are several reasons for doing this, but the most important one is it gave us a faster build. Because although the compiler is now doing more work, because it's doing the instruction selection that the linker used to do, it means that it only does it once for each library. And so every time you, in the old world, would link in the FUMP package, for instance, it would do instruction selection for printf every time, which is clearly silly. Now we do it once, and the linker doesn't have to. And so the compiler slowed down, but the build's actually sped up. And the assembler can use the same design and use the obj library. But the key point about this step is we didn't change anything for the user. The input language is the same, the output is the same, it's still a binary, but the pieces are different. So this is the old diagram I showed you, right? Compiler, assembler, link is the grand old scheme. The Plan 9 world has the compiler driving the linker or the assembler driving the linker. As of 1.3, it changes to this. And let me flip back and forth between these little so you can see the difference. I'm sorry, I don't animate slides well. And you can see what's happened is we now have a much more traditional linker. It's getting real instructions because the obj library that does instruction selection has been moved from the linker into the back end of the compiler and the assembler. And so now the assembler and the compiler are somewhat closer to the old scheme if you include the assembler as part of the process. So the new Go assembler is a weird thing. There's really nothing else like it. But what it does is take in textual descriptions of pseudo instructions and generate real instructions for the linker. So 1.5, the big step, we're getting rid of C. So we've done a lot of prep with 1.3 and 1.4, but now we actually finished the job. So Russ wrote a translator that generated Go programs from the old C source for the Go compilers, and also for the linkers, by the way. And the old liblink got rewritten into a suite of libraries, which we're collectively calling OBJ here. And so there's a thing called OBJ, which is the portable part, and then sub-directories of that contain machine-dependent parts that know about the details of each architecture. And there's been a couple of previous presentations about this work. It's an interesting story in itself. Russ gave a talk at GopherCon 2 years ago, but it's quite out of date. We actually did something quite different from what he talked about. And then in GopherFest 2015, I gave a higher level but more accurate view of what really happened in 1.5. So the compilers now, instead of being 6G and 8G and all these other weirdly named guys, they all became a single program called compile. And so you run go-to-compile, and you configure it literally by setting the standard environment variables, which are officially pronounced goose and gorch. Now, we did the same thing for the linker. You got to go to a link. So you set your goose, you set your gorch, and now you can compile your program, right? But some of you may be thinking, how is it possible for a single compiler to handle all these architectures? We know that cross-compilation is really, really difficult. Well, actually, it's not. You just have to plan for it. The thing to notice here is there's only one input language. It's called Go. And as far as the compiler is concerned, there's really only one output thing, which is those pseudo instructions in binary form that are being delivered to the OBJ library. So all we have to do is configure the OBJ library using the variables when the tool starts. I'll show you how that's done in a minute. Now, for the assembler, we actually machine translated the assemblers from C to Go, but it was messy and I didn't like it. So I proposed that we write a single program from scratch to replace all of them, do it in Go, and replace all those assemblers with a single program, the Go tool as them. And again, Goose and Gorch are going to do all the configuring. But there's a question you might have here, which is that assembly language isn't Go. Every machine has a different set of instructions, a different set of registers. It's not one output language. How are you going to fix this? Well, in fact, they are kind of the same. Let me show you. Here's an example program. This is a simple program that just adds 2 integers and returns the sum. I'm now going to show you what the compiler prints out as pseudo instructions if you ask it with the -s flag to show you the assembler. And I've trimmed a lot of the noise. There's a lot of noise if you do this. But these are the instructions that actually come out, pseudo instructions, that come out of that phase of the compiler. Here's the 32-bit. Don't worry about the details. Again, just take the gestalt. There's a 64-bit x86, also called AMD 64. There's the 32-bit ARM. There's the 64-bit ARM. There's the System 390, the IBM machine, which is new to us, but certainly not new to the rest of the world. There's a 64-bit MIPS. There's a 64-bit Power. You notice there's a kind of similarity here. It's because they're really all the same language. Partly that's by design, because we've just kept using essentially a national 32,000 assembler for the last 30 years and just changed the machine underneath. But also because at some level they really are the same. They're just instructions and registers, operands, literals, labels. It's all the same stuff. The only real variation that matters is that the instructions have different names, the registers have different names, and sometimes the offsets vary, but that's just a feature of how big the word size is on the machine. So this all goes back to Ken's National 32,000 assembler. That is National 32,000 assembler language, as Ken thinks of it, adapted to a PowerPC today. And so we have all the pieces we need, because we really do have a common input language. We have the OBJ library for the back end, so we can write an assembler. Now, there's a problem with doing this, which some people object to, which is that if you go to the national or the PowerPC manual and look at the assembly language, it doesn't look like this. It's got different syntax. Sometimes the instructions have different names, because these are really pseudo instructions at some level. We don't really mind, though. To an outsider, it can be really off-putting when they see Go's assembler and how odd it looks. All those capital letters and weird stuff. But because we have this common assembly language across all these machines, we get a tremendous result, which I'm arriving at. And so we think that's a trade-off worth making, and it's not very hard. Plus, once you learn how to program a 68,000 in Ken's assembler, you can program a PowerPC. What's the difference? So how does this work? The 1.5 assembler is I like to think of as the apotheosis of assemblers. You give it any machine you want, and it'll assemble it for you. It's a new program. It's written entirely in Go. It has a common lexer and parser that just takes the input language, whatever you give it, and then turns that instruction, parses it into a data structure, which describes the instruction in a binary form, and delivers that to this new OBJ library, which has machine-dependent information in it. And the core of the assembler, most of the code, is actually completely portable. It has no interesting information about the machines. But there's a table that tells you what the instruction names are. There's a table that tells you what the register names are. And there's a few fiddly bits around how operands work, but it's pretty straightforward. And all of this is configured when the program starts by looking at the value of GoArch. Now, Goose comes in with some very, very subtle corner cases that I don't want to get into. The fundamental part comes out of Gorge. And there's this internal package to the assembler called Arch, which creates these tables on the fly by extracting them from the OBJ library dynamically. And here is some real code. This is slightly reduced for simplicity, but the core of it is this. This is the Arch package inside the assembler. This is the routine that sets up the entire assembler for an x86 architecture. This actually handles both 32-bit and 64-bit. They're the same from this point of view. And all we do is we loop over all of these. Can I do this? Yes. That's a loop over the register names that have been coming out of that are in the OBJ library defined in the x86 package for the OBJ routines. And we just set up a map that maps from names of registers to their binary code as the OBJ package knows about them. And then we do the same things for the instructions. And here, these codes are not actually instruction codes if you know assembly language. They're not whether in the manual. It's literally an alphabetically ordered enum for all of the things. Because remember, these are really pseudo instructions. They're not the real thing. But now we know all the names of all the registers and all the instructions. And so the architecture description we're going to return just contains these two maps. Here are the names of the instructions you recognize. Here are the names of the registers you recognize. And a few other details, which I've elided, but they're pretty straightforward. That's all the information you need to assemble for those machines. In fact, the parser just does string matching to look up what the instructions are. You're in column 1, there's a word, that's an instruction. Look it up in the instruction table. It's really simple. Can I get this to, oh, great. No, why am I editing this? There we go. I didn't even know I could do that. Here's an example. Here's the add word instruction on a 386 that you might write in real code or see come out of the compiler. It says add W, AX, BX. The assembler knows the first column is the instruction. So all it does is look inside the instructions list that's inside the architecture structure and indexes the map by add W and gets a code. Puts that in the A name, which is a weird name, but that's what it is. And then there's from and to are the two operands. And again, look up the register as an AX, look up the register as BX. It's more complicated than this, but that's the essence of it. You just look up these words that you see in the input, stuff them into a data structure, and pass them to the OBJ library. The point is, this is just text processing. The assembler is just doing text processing. It doesn't know anything about the semantics of these machines, really, at all. Now, there's some validation it has to do. It has to make sure that they're lexically and syntactically correct. That's easy. That's just standard parsing techniques. And so it also verifies things like operands, do they belong. There's a few tweaks in some ugly corner cases because some of the machines have weird operand modes that the others don't, but they're fairly easy to apply. It's not a big deal. The key point is that all of the semantic checking is done by the OBJ library. And the basic rule is if the prog structure, which describes an instruction, goes into the OBJ library and there's no error, it's because the OBJ library knows how to turn that into an instruction for the real machine. And so if we can parse it and the OBJ library likes it, we're done. That's the whole idea. Now, this is obviously crazy, but it works, and we can test it and prove it. So the way we did testing was, remember, we had the old assemblers still around. They're written in C. And so literally, we took programs. I wrote the assembler with the OBJ library behind it. We put it together, and we take the same program, we compile it with the old, we'd assemble it with the old assembler and the new one. And we iterated until the new guy got exactly the same bits out that the previous one did. And then went on to the next program. And by the time we'd done the whole standard package, we had a working assembler. And that was pretty much it. That's kind of A/B testing is just an amazingly great way to test stuff. And it worked out really well. I did the 386 first. Then I did the AMD 64, and each time I had a little bit more special casing, but it got better. By the time I got to the PowerPC, it was actually just like a couple hours work to do a new architecture for this assembler. It was so easy. The most exciting and I think interesting part of this whole thing is at no point in the writing of this assembler that handles these 4 architectures did I look at a single hardware manual. This was entirely a text processing problem based on the knowledge that the OBJ library knew all this stuff and I didn't have to. That's kind of cool, I think. So the result is we now have a single Go program that replaces many C and YAC programs, each of which was different. So it's much easier to maintain. It's much easier to maintain one program than many. It's also much easier to fix bugs once rather than in every program that might have them. Because it's a Go program, it can be tested properly. That's nice. It's dependent on a library that the whole world depends on. And so correctness is almost automatic, which is very nice. That's overstating it, but there's a big component there that's true. And we have a new assembler that's almost exactly compatible with all the old ones. The places where it's not is mostly where the previous assemblers had diverged and had slight variations in how certain things worked. But we just completely unified it now. We've made it a truly universal assembly language for all of them. And portability is really easy. I showed you, I think, all of the architectures that it can handle today when I went through those examples of the add function. And a large number of those were actually provided by the open source community. And if you look at the Git repository and look at the check-ins that added those new architectures, you'll see that they're actually getting to be quite small check-ins to add all the information you need for a new machine. It's actually quite lovely, and I think a validation of the approach. And I love that the open source community is now adding architectures so easily. Now, as I said, you configure the assembler by loading essentially tables that are known to the OBJ library, which is the encoding of the machine architecture. Well, can we generate tables? I don't like writing tables by hand. Well, not quite, but listen. The disassemblers, which are not what I'm talking about, but they're used by GoTool, pprof, and some other pieces. They're actually were created, at least, I think all of them, but at least some of them anyway, by Russ one board afternoon, when he wrote a program that would take in the PDF of an instruction manual and turn it into the bit patterns that are needed to encode instructions. You have a machine-readable description of the machine, why not read it with a machine? And so the disassemblers are machine-generated. And it's a little tricky to go the other direction. It's not as easy. And first, one thing, it has to be absolutely right. If a disassembler is wrong, it doesn't really matter that much. You'd like it to be right, but corner cases aren't as important. For the other direction, it's got to be 100% perfect. And so it's a much harder problem the other way. But Russ is working on it. And I hope we'd have it done by now, but we don't. But I hope by the end of the year, you'll be able to give us the instruction manual PDF for a new architecture, and we'll be able to turn the crank and give you a working assembler. That's the goal. So that means we have a largely machine-generated assembler, at least once this handwritten part up front is done. So in conclusion, I think despite what people will tell you, assembly language really is essentially the same everywhere. And we've moved to the point in the world of portability where we should treat it that way. And we can use those ideas to build a true common assembly language that lets you talk to the machine at the lowest level and yet not have to learn a new syntax and a new tool every time you want to do that. It also makes it much easier when you have a single environment like this to have the compiler interact with it and the linker interact with it in a way that's nice and transparent and straightforward. And you can do this by dynamically loading tables that are machine generated on the fly from a couple of environment variables, which is, it's a shame we need two, but we do. And one day, maybe this year, I hope, we'll be creating those tables automatically from machine. And so we have taken what is arguably one of the most non-portable things out there, which is assembly language, and we've constructed a portable solution to it. And that's the Go way. Thank you.